Why should we connect SystemModeler and Wolfram language to our system? And what are some interesting use cases for that? We will move on to the how. How can this be done? And introduce the enabling technology, the OPC UA standard. We have a SystemModeler library for that, the Wolfram OPC UA Library. And we will take a look at the current state, what is available today. And we are currently working on updating it, and we will take a sneak peek on some of the new features in the upcoming release. So, starting with the why, let's look at some interesting use cases. We start with data collection. Here, for example, we have a lab-scale bioreactor, a device made to support the biologically active process. Maximizing the yield from these kind of processes requires good control of environment conditions like temperature, pH levels, oxygen levels, and many other parameters. By connecting to it, we can collect the data that is relevant for our particular process and do post-processing in Wolfram language. We can do various kinds of data analysis or create data-driven models, like for example, use the data to train a neural network. But what's the point of training a neural network unless we can put it to good use? So let's move on to high-level control and user interfaces. We can take the trained network and import it into SystemModeler. With our model running in real time and connected to the system, we can feed the sensor data into the neural network and use the output to control the system, thereby running the neural network against a real system in real time. We can also prototype and develop other high-level control algorithms and run them in real time against a real system. Using the Wolfram language, we can build dashboards and custom control panels. This can be useful, for example, in a lab setting, where you might do a wide variety of different experiments using the same equipment. You can then build control panels that are targeted to the needs for operating and monitoring a specific experiment. Another broad area of applications are digital twins, software in the loop, and hardware in the loop simulations. Say we are writing PLC code to control our system, and we want to test that PLC code before deploying it to real hardware. If we have a model of our system running in real time and we can connect that to our PLC simulator, then we can run software in the loop simulations and test our PLC code before deploying it to actual hardware. Likewise, when we do deploy our PLC code to the real hardware and connect that to our simulation, we can run hardware in the loop simulations, enabling us to conduct more tests without access to the real system. We can also leverage other Wolfram technologies. For example, we can run the system through different scenarios and use the soon-to-come system model validate functionality to validate that our PLC code fulfills all specified requirements. So the standard that makes this possible is OPC UA. OPC Unified Architecture is an open standard for industrial automation communication that enables data exchange between devices, applications, and systems. The standard is developed by the OPC Foundation, and the name Unified Architecture comes from that it unifies all of its predecessor standards into one. In contrast to the predecessors, OPC UA is a platform-independent standard and designed to run on everything from small devices, like PLCs, up to regular desktops and cloud servers. At the core of the standard, we have an information modeling framework and services for browsing and accessing data, as well as receiving data and event notifications. The information modeling framework is object-oriented and includes constructs like hierarchical composition, object types, and type hierarchies. It makes it possible to standardize information models for industrial equipment and increasing interoperability. All the services in the standard are defined in an abstract way and then mapped to existing communication protocols. This makes the standard very flexible in that it can easily adopt new communication protocols as they emerge. Standard information models for various industrial domains are published separately from the core standard and are called companion specifications. Here we have a few examples. As we can see, there is a large automation presence in energy, building, factory, and process automation. However, there is also representatives from very different domains like mining equipment and laboratory and analytical devices. In all, there are over 60 published companion specifications. For connecting SystemModeler models to OPC UA servers, we have the Wolfram OPC UA Library. It's available to SystemModeler users as a free download from our library store. In the library, we have one block that represents a connection to the server, and that's also the place where you can specify connection parameters, like the server URL. It is of course possible to have several instances of this block so you can connect to multiple OPC UA servers from the same model. There are specific blocks for read and write requests, and they are available in variations for working with scalar values of type real, integer, and boolean. Common for all read and write blocks is that they have parameters for specifying which node ID to read from or write to, and they must also be connected to a server block. In OPCUA, a node ID can be either a numeric integer ID or a string ID. The library supports both of them. OPCUA has a richer list of types than Modelica. For example, it has unsigned and signed integer in all combinations of the usual width variants, whereas in Modelica we only have integer. So when writing data, we must also specify the OPCUA data type that should be used for the write request. So how does it scale to read and write one single node in each request? In the plot we have the number of nodes on the x-axis, and on the y-axis we have the minimum sampling interval we can have, while still maintaining real-time synchronization in the simulation. The curve in blue represents making a separate request for every node, and as expected, that scales linearly with the number of nodes we want to read. Now the problem is the steep slope due to the overhead we have on every request. Common scenario, if not the most common, is that you want to sample all the data with the same sample rate, and in that case it's completely unnecessary to make one request per node. We could get much better performance if there was a way to read or write several nodes in the same request. This is something we are addressing in the upcoming version. The solution is new blocks for writing or reading a list of nodes in a single request. The nodes to write to are still defined by individual blocks, but by connecting those blocks to a list block, all connected nodes will be written with a single request. And as we can see in the plot, that gives us significantly improved performance. In secure OPCUA environments, verifying the authenticity of clients and servers is critical to prevent unauthorized access, data tampering, or network attacks. The new version of the library will introduce support for client-server authentication and message security in the form of the two security modes: sign, where messages are signed to ensure data integrity and authenticity, and sign and encrypt, where they are also encrypted to ensure confidentiality. For user authentication, we will add support for username-based authentication and certificate-based authentication. In OPCUA, status codes are used to indicate the state of requests and the quality and state of data values. Status codes comes in 3 different severity levels. They can be good, uncertain, or bad. They can also carry additional information about the reason why the status isn't good. For example, maybe the value is at the limit of the sensor's operating range, or the communication with the data source has failed. In the current version of the library, the simulation is aborted as soon as something isn't good, so the user has no control over the error handling. In the upcoming version, all the new list-based blocks for reading and writing will have an extra output, the severity of its current status. They will also have parameter to control the block's built-in error handling, where the possible choices are error on status severity uncertain and bad. This matches the current behavior of the library. Error on status severity bad. This means the simulation continues with the uncertain values. And the third one is report status changes. In this case, the simulation continues regardless of the status severity. Selecting any of the last 2 options means we can do error handling in the model. Maybe the bad value isn't that important to our operation, or we can shift to a different operation mode to remedy the situation. To aid in the decision making, the blocks will also come with a timestamp output, so that it is possible to take different actions depending on how long the value has had that particular status code. Selecting to only report status changes will also mean that the simulation will automatically reconnect to the server in case of the connection goes down due to network issues. So to conclude, the new OPCUA library will bring improved performance and scalability with the new list-based blocks. The new security features and configurable error handling will empower users to build robust and secure applications on top of the library.